Well, good afternoon. This is about 4:29. We're about a minute early getting started, which will be a new record for this class because I used to never be able to get over to the Birmingham East Campus in time to start on time. But now that we're doing virtually, I was here already. So I saw Rance's name show up. I guess you're still there, aren't you, Rance?
Yes, sir.
All right. Can you see the white screen?
Yes, sir.
Okay. I don't know how we're going to go back and forth between screens like I used to in class because I think I have to go through all sorts of gyrations to do so. So I may minimize doing that, but we'll see what happens. This will be our first time. Is anyone else there besides Rance?
Tamika Hamilton.
Okay, let me get your name. Did you say Addison?
Tamika Hamilton.
Oh, Tamika, got it. Okay. Tamika's here. Anybody else? Just Tamika and Rance? Okay. Well, I'll pick up others as they come in, hopefully. I'm guessing it's about 4:30 now. Ooh, 4:31. Let's get started. Are there any questions either about how we're going to do this, how things are going to work, anything such as that? Okay. Just a little bit of background. If you notice in the lower left corner, you'll see there, sure enough, is the recorder. I'm still going to be recording these things, putting them on YouTube videos, and then they'll be accessible through Blackboard. It has been taking at least overnight to get this class out there. Sometimes it's taken several days, but it seems like it's moving faster here at home than it did at work. So I'm still recording the class. We're still doing everything the same way we did before in class. The only difference is that it might be harder to go back and forth between the PowerPoints from the book and the blank PowerPoints where we work on examples. If it gets to be too big of a pain in the neck, I'll stop using the one in the book or wait till the very end of class or end of a chapter and then show all the PowerPoints there at once. We'll see how it works. All right, any questions? All right, now my memory is we're in chapter 16, Wave Motions and Sound, which is a very important chapter for you guys because you're going into sonography. Now right now we're still in the general portion of the chapter, but the very next section we go into sound waves. Not that the specific things we'll be doing will be all that applicable, but everything we do with wave motion, sound, frequencies, all these kinds of things, they are important to you. Hold on just a second. Sorry, I had to close the door. My wife's working remotely downstairs. She put me upstairs so I wouldn't bother her as much because I talk so loud. So anyway, I forgot to close the door when I came in here the last time. So, where I have that we were was chapter 16, Wave Motions and Sound, and we're right at the end of 16.2, and 16.2 was a long section. 16.1 was characteristics of waves, and 16.2 is, well, oh, not that long a section, electromagnetic waves. Yeah, only one example here. No wonder I didn't see it was on the previous page. So, one example here, there will be a figure that I'll show, but if it's too big of a pain in the neck to go back and forth, then I'll hold off all the other figures until the end of the chapter and then go back and review them. So let's do example 1, as long as there's no questions, right? Okay. The FM band of a radio is centered around the frequency of 100. Let me get my pen set up. Okay, the frequency here is 100, and that second zero is significant, so that means all three are significant. Megahertz, M-H-Z. Now, just right off the bat, here we have a metric prefix. Most of the time we're going to want to work with hertz, okay? So we're going to have to change the megahertz to hertz. So let's do our unit conversion right here while we can, and we're going to change this to hertz. And by the way, the hertz is the same as a per second, or 1/2, or second to the -1. The book uses, well, it uses 1/2. Okay, so I'll put a 1 up here, per second. Okay, now, what is going to be our conversion here? Remember, we always deal with the units first, then we'll deal with numbers. We're wanting to go from megahertz to hertz. So which one's going to go on top of the line? Which one's going to go below the line?
Which example are we working on? 1?
Say that one more time.
What example are we working on? Example 1?
Okay. This is, yeah, example 1. Is that what you're asking on page 434?
Okay.
Yeah.
Let's make sure I'm on the right one.
Okay, you're right. Okay, we got to get from hertz to megahertz to hertz. One unit goes on top of the line, one goes on the bottom. Which goes where? Help me out here. Come on, make a guess. Name a unit. Either megahertz or hertz. Pick one. What'd you say?
I'm trying to set my computer up, but I
Oh.
hear you.
Well, I hear you well. Okay, pick a unit. Hertz or megahertz, either one. Anybody, help me. By the way, if anyone else comes into the class, for some reason I'm not seeing pictures. I saw one name and that's all. So I don't know why it's limiting what usually it lists, like yesterday afternoon I had 4 people, had more than that in the class, but I could see 2 or 3 at once, Now I'm not seeing anybody. So you pick a unit, hertz or megahertz. Anyone? Pick a unit. Huh? Okay. I hear talking, but I can't make out what you're saying. Pick a unit, any unit, hertz or megahertz.
We're going from hertz to megahertz, right?
Yeah, you're going from megahertz to hertz. So pick one of them. I don't care which one.
Hertz.
Hertz. Okay, where does it go? Above the line or below the line? You see my ball bouncing up and down on the screen? The little dot?
Oh, yeah.
Okay. Does it go above the line or below the line? Hertz.
Above the line?
Above the line. You're absolutely right. You win. Ding, ding, ding. Okay. That makes megahertz going below the line. Okay. Why is that? So if I could get my pen to write, it's been doing poorly all day, we can cancel out the megahertz. We don't want megahertz. We want hertz. It's exactly what we want. But now we have to figure out how many hertz are in a megahertz. Another way to look at this, what does that metric prefix capital M mega stands for? Anyone remember? Hint, it's a multiple of 10. What multiple of 10? Okay. Decahertz would be 10 hertz. Hectohertz would have been 100 hertz. Kilohertz, now that makes more sense. That would have been 1,000 hertz. But after that, we do by powers of 3. We don't do by powers of 1, powers of 3. After kilohertz is megahertz, so how many would that be? 10 to the 6. 3 is kilohertz, 6 is megahertz, 9 is gigahertz, 12, I mean, they just keep on growing, but they go by powers of 3 after you get to kilohertz. So 10 to the 6 hertz is 1 megahertz. Mega means a million. 10 to the 6 is a million. Okay? So what does that mean? Multiply numerators. You have 100 times 10 to the 6th hertz. That's what 100 megahertz is. Now, if you don't like having 100 out there, you can move the decimal 2 more places to the left and make it 1.00 times 10. But if you moved it 2 places to the left, you bump it up by 2, 10 to the 8th hertz. And that's our cycles per second, per seconds. Okay? So either one of those will work. Okay? 1.00 times 10 to the 8th probably makes more sense. Now my pen isn't writing well, so I'm going to try to erase some of the stuff where I've written a second time that erased too much. Okay. 10 to the 8th. Okay. That was the first thing they gave. Okay. FM band of a radio is centered around a frequency of 100 megahertz, which is the same as 1 times 10 to the 8th hertz. Find the length of an FM antenna if each arm must be a quarter of a wavelength. A quarter wavelength. Okay? And the hint here, first find the wavelength. Now we had a formula before. If you flip back one page, you'll see that in the middle of the page, or no, at the bottom of that previous page. What is that formula that relates wavelength and frequency? You see it? In a little green box on page 433. Bottom of the page. Anybody? Yeah, you see it? Say it one more time.
C equals lambda F.
That's it. C is equal to lambda F. Where lambda is the wavelength, that's what we're looking for. Find the wavelength. So this is what we're looking for. The unknown here. It's not ultimately what we're looking for, but it's what we're looking for first. So let's go ahead and tell me something. We know frequency is F, lambda is wavelength. What in the world is C?
Speed of light.
The speed of light. And we'll go back and get that number in just a minute. Okay? So let's solve this equation here for lambda. How would we do that? We want to isolate lambda, get it by itself. How do we do that? Help me, somebody. How do we do that? Isolate the lambda. What do you need to get rid of? What's messing up the lambda here? Isn't it the frequency? How do you get rid of the frequency? It's multiplied by the wavelength, so how do you undo multiplication? Divide by frequency. But if you do it to one side, you got to do it to the other side as well. So that wipes out the frequency on the right-hand side. So now we have our formula. Lambda is equal to C divided by frequency. Well, you just told me Goodness gracious. C was the speed of light. Turn back that one page again and get what the speed of light is. That is 3.00 times 10 to the 8th meters per second. Now I think you probably see why we wanted this in hertz, which is per seconds. Okay? Divide that by our frequency, which we just determined to be 1.00 times 10 to the 8th. Oh, that worked out nicely, didn't it? And my pen's not writing. This is so frustrating. 1.00 times 10. If I write slowly enough, it picks up. And this is in per seconds. 1/second. Per second. That's what a hertz is. Okay? Well, hopefully you'll see the per seconds disappear, and the 10 to the 8ths disappear, and 3 divided by 1 is pretty easy. Is 3. 3.00 meters. Can't get my pen to write. 3.00 meters. Okay? That is a wavelength. But the problem said, find the length of the FM antenna if each arm must be a quarter of a wavelength. So if this is a wavelength, this is equal to 1 wavelength. Okay? What would be a quarter of a wavelength? What would you have to do? Divide by 4. Divide both sides by 4. And what you have then, if I can get my pen back, my picture back, is 3 divided by 4. If you put it in decimals, that would be 0.750 meters. Okay? That would be the length of each arm. Okay? Now, I don't know how many arms the FM antenna has. I always pictured it having 2, so I would have doubled that, but the book doesn't. It just does 0.750 meters. Okay? The point is, the main thing was finding that wavelength, and then since it was a quarter wavelength, that's what you did. Okay, now 7.750 meters, if that is the SI unit, so that's what you would leave it. Picture this. The meter is from your right ear to your left finger if you hold your hand out perpendicular to the body, or left ear to right index finger, you know, if you hold your arm out perpendicular to your body that way. That's 1 meter, so about 3/4 of that. That would probably be from your finger to maybe about your shoulder. That would be 7/5. So that would be how long each arm of the antenna should be if it's an FM antenna. And that kind of makes sense, doesn't it? All right. Now, here's where they want us, or it would be ideal to go back and forth between the slides. Let's see how awkward this is. I'm afraid it's awkward, but I'm going to try it and see what happens. Remember, I had to do this in class all the time, and that was awkward in itself. Okay? What I'm going to do is go to the graph PowerPoint. No, that's not the one. The Chapter 16 PowerPoint. That's the one I want. Okay, and then I'm going to open that. I need to do slideshow to current slide. Okay. Now my question to you, can you see this graphic now? It says the electromagnetic spectrum and it has a red line. Do you see that, or did you lose it? You can see it?
Yes, sir.
Excellent. Okay, Rance, can you see it too? Are you still there, Rance? Okay. Can you see the graphic?
Yes.
Excellent. Okay. Is anyone else there yet? Who is this? Okay. I still didn't get your name. What is it?
C.
One more time.
C.
Spell it again. Reese. Is that what you said? No.
No, T.
Oh, T. I know. Okay, I got you now. Yeah, there you are. Miss Pettigrew, right?
Correct.
All right, now I got you. Okay, I got 3 people there. Any more? Okay, welcome to the class. You may have been here for a while. I didn't hear you earlier. Okay? Now, here is the electromagnetic spectrum. Okay? The thing to note here, besides just being of interest, okay, your low frequency waves, and I'll just tell you this off the top, this also means low energy waves, okay? Down here, your broadcast band, that would be your AM radio, okay? Shortwave radio would be in here. If any of you happen to be ham radio operators, you probably operate in the shortwave, range. The TV bands, that's where FM and TV is usually in about that range. There was 10 to the 8th. That last problem, we were right in that area. Then microwaves are over in this area. Big broadband here. Now, if I'm not mistaken, most of the cell towers that you see out there are signaling things in the microwave range of things. So that's what's happening there, and it's a really broad range. So that's why you have so many cell towers, so many of those antennas or whatever they are on there that they can send and receive and transmit those microwaves. Then you're getting into what we call the infrared. Okay? Well, infrared, probably not too good a definition of that, would be heat energy. That it is pretty much what it is. Then look at this narrow little band here around 10 to the 14 to 10 to the 15. That's the only part of the visible light spectrum. Now in between there's you have red, orange, yellow, green, blue, indigo, and violet. That's Roy G. Biv. That's your visible light spectrum. If you put visible light through a prism, it will split it into those colors. The colors of the rainbow, by the way, because raindrops act like little prisms. That's why you see a rainbow occasionally. That's the only part of the rays that come off the sun that our atmosphere lets come in freely. Now, sure, some infrared probably sneaks through, and some ultraviolet definitely sneaks through. But that's the main part that comes through. Now, how do we know ultraviolet comes through? People get skin cancer. People get cataracts. Their skin wrinkles, okay? All that's caused by ultraviolet radiation, okay? A little bit of that does make its way through our atmosphere, but most of what comes through is visible light. Okay, backing up a little bit. I'm just guessing, if y'all were to go out to your car right now and open your car and get in, it would probably feel hot in there or cold in there. Any guesses? Go out and get in your car. No, don't go out now. But if you did go out and get in your car, do you think it would be warmer than the outside or colder than the outside or the same as the outside? Just make a guess. The same? You have any wind?
It's cooling off right now.
Okay, but I bet you your car is warmer than that, especially if the sun's been shining on it. Haven't you been out in the summertime, you get in your car and it's burning hot? Have you ever experienced that?
Yes.
Yeah, okay. Now why is that? Because that visible light comes in through your glass of your car, But when it comes through the glass, it loses a little bit of energy, which means it goes down in wavelength a little bit. I mean, down in frequency a little bit. It increases its wavelength. Okay, that's the next thing I want. Can't get this thing to get out of there. Oh, yuck. There we go. So it decreases its frequency, which actually is increasing its wavelength. It gets a little longer down here. Well, where are you into there? Infrared radiation. That's heat. Now that infrared radiation doesn't have enough energy to make its way back out through the glass. So you're trapping the heat in there, and that's why the car gets so hot in the summertime if you don't leave the window cracked or something. That's why you do not leave small children or pets in a car, closed car, in the summertime out in the heat, in the light, because it will get so incredibly hot they can suffer serious problems. Okay? So that's, and you know what we call that? The greenhouse effect. Have y'all heard of that recently? That is what they blame for causing global warming. The fact that light comes in from the energy comes in from the sun, invisible light, it loses a little bit of energy when it comes in, it lengthens to be infrared. The infrared cannot make its way back out, so the earth builds up heat. Okay? Now we do that anyway. Our atmosphere does a good job of that because we're far enough from the sun that in general we would be too cold to support life. But because our atmosphere is there and trapping that heat through this very process here, we have warm enough temperatures to support life on the planet. Now, started off by going beyond the visible light spectrum, ultraviolet, that's the dangerous and harmful because it's higher energy light. And that indeed causes skin cancers. It causes cataracts. It causes wrinkling of the skin. If you've ever seen these people that back in their youth were the sun worshippers, they got out there and laid around in the sun as much as possible and got just as brown as they could, thinking that was really healthy because sunlight gives you vitamin D. Well, a little bit is all you need, but you know, they were getting plenty of it. Well, in fact, you know why you get a suntan? Why your skin turns darker? Because your skin is trying to protect you. It's moving the melatonin up to the surface so that it blocks some of that ultraviolet radiation coming in. That's why you get a suntan. And that's also why you get a sunburn, because that high energy ultraviolet radiation burns your cells. And that's why you get a sunburn. The suntan is trying to keep that from happening. Now, some of you folks have more melatonin than I do, and you're spared a little bit of that. You're not nearly as likely to get skin cancers as I am. I've already had one small basal cell removed, and my future is not very bright because I put on sunblock every day, even days like today when I'm not going out very much, put on sunblock every day to keep from damaging any more skin tissue. Okay. But it also causes all these other things. What I was saying about those people who laid out in the sun all the time, if you look at them in about 20, 30, 50 years, they're going to be the prunes. Their skins are going to be so wrinkled, so wrinkled up that that nice, beautiful tan, they'll say, nope, that wasn't worth it. Okay. But anyway, that's higher energy radiation, ultraviolet. Most of that blocked by our atmosphere, but not all. Then you get on higher energy, higher frequency, and you get into the X-rays. Okay, now we think of X-rays as what they do when they're checking for broken bones or tumors or other things like this, and indeed they do. But guess what? You don't want to do very much. I mean, even going to the dentist, they'll take X-rays of your mouth. But they use just as low an energy X-ray as they can and minimize the amount that they're going to turn on. And I guarantee you those technicians will get out of the room. Have you ever noticed this? and go behind a dark window and then turn on the machine. You know why? They're exposed to this every day. They're trying to protect themselves, and I bet you every one of them, somewhere on their body, they have a badge. And the badge is going to detect how much X radiation they've been exposed to. They have to mail that in to somebody, the health department, somebody, every month. And if they get too much radiation, they can't go back to work, okay, because of that X radiation. Now you move on up the energy level, you get to gamma rays. You don't want to mess with gamma rays. They are deadly. In fact, when you have a nuclear explosion, like a bomb or just a nuclear power plant that explodes, sure, there's got a lot of heat that's going to be produced. Yeah, that's going to kill a lot of people, okay? But what kills more is the exposure to the gamma rays. And the sad news there is they're not going to kill you immediately. They are going to penetrate your body. Nothing's going to stop them. Bone tissue, nothing will. And they are going to be destroying cells as they go. And you get what you call radiation sickness. And that is a long, slow death. I don't know if you remember, it's probably been 10 or 15 years ago, that there were some Russian spies that had defected to England, United Kingdom, and the man and his daughter were out having a meal or a drink or something at an establishment, a pub, something like that. I think they were sitting outside, and a Russian agent dropped some radioactive material into their food or the drink or something, and at least one of them died, maybe both of them did, and it was not a pleasant death. Okay, it was miserable because they were being destroyed from the inside out because of those gamma radiations. You don't want to mess with gamma rays. You don't want to mess with X-rays. They're necessary, but only in small doses, and you don't want to mess with ultraviolet rays. Put on those sunshades, that sunscreen. Put on the UV protective eyeglass, sunglasses. You don't want to damage. I've already had both my cataracts removed, and one in each eye. A small basal cell removed. It's just a matter of time, and I'm getting more wrinkled all the time. That's because I've lived longer and longer in the sun. When I was a young boy, I lived on a farm, was outside in the sun all the time, driving the tractor or doing whatever, baling hay. Sure, I wore a hat or whatever, but still, I was exposed to way too much ultraviolet radiation. Now, so as you go to left to right, your frequency is increasing, your energy is increasing. But because of that relationship, remember that C is equal to lambda F. Isn't that the one you gave me earlier? Yep, remember? You could rewrite this as lambda, like we did, is equal to C over F, right? That means it's an inverse relationship. As your energy is going up, your frequency is going up, your wavelength is going down. That's why for high energy, very short waves, where low energy is very long waves. This is 30,000 meters long. This is 3 times 10 to the minus 10. That would be 0.000000003. That's how long that wavelength is. This one down here in the low energy, 30,000 wavelength, 30,000 meters long. That's a long wavelength. Okay, so there's the relationship, the inverse relationship between wavelength and frequency. As the frequency goes up, the wavelength is going down. As the wavelength is going up, the frequency is going down. Inverse relationship. All right, any questions on that? Now that's the end of 16.2. We only had one example, but they came up with 17 problems, okay? So I would do some of the odds for any of those problems. Any of the odds 1 through 17. Most of those have answers in the back. Go for it. There is on page 435 also a physics connection evading radar. Radar is actually radiation detection, okay? Radio detecting and ranging, that's what radar stands for. And this is a type of airplane called the stealth bomber. It's designed to be as close to invisible to radar as possible. They do that by the materials they use and all sorts of things like this. They talk about some other devices, a French fighter plane known as Rafale or something like that. Various things they do to try to avoid being detected. That finishes 16.2. Any questions on 16.2?
No, sir.
Okay. Let's move to 16.3. Now that's going to be on the bottom of the next page. I think we're going to have to do a few problems before that table's going to make sense. So let me see if I can come down here. I'm going to discard that and go back to this and go back to current slide. Okay, can y'all see the white screen now? Yay or nay?
Yes.
Oh, good. In one of my other classes, when I changed, they lost everything and I had to go back and reload. But I'm glad y'all are able to see it. 16.3, this is probably the most important section to y'all, sound waves. Now, not everything we're going to do in this section is going to pertain to diagnostic sonography, okay? But it relates, just like frequency, wavelength, all that relates, okay? This is more talking about sound that we detect with our ears. And you're talking about ultrasound, which we can't hear with our ears, but still it follows the same principles. Sound refers to those waves. Whoops, let me get my pen back. Okay. Okay. Refers to those waves transmitted through a medium I don't know if my pen's going right or not. It stopped writing. Oh boy, what a pain. Say again? I can't hear you. Can you see what I'm writing? Or did someone else come in the class? Hello?
I can see what you write.
You can, okay. I thought I heard someone saying something. Through a medium, I just can't get my pen to write. It just quit writing. I've been thinking it's because of, I think my pen may have died, okay? It's not picking up anything. Okay, every now and then I can make a, goodness, this is going to be a pain in the neck. I was thinking it was all the programs I've got open. It may be, it's just run its course. This is an electronic pen, ionizing pen they call it, and evidently it has quit ionizing. Man, what do I do now? Well, I'll tell you what I'm going to try to do. I hate to do this. I'm going to do a Control-Alt-Delete and see if everything seems to be okay. So let's end that. Now let's see. Okay. If I try writing with my finger on the screen, that's going to be pretty ugly. But I can't get my pen to pick up. So I'm going to try something else now. I'm going to do Control-Alt-Delete again. And I think I'm going to what I'm going to do is close this one. See if that did. Whoops. May have closed the wrong one. Okay. Okay. Oh, Jamal, are you there? Okay. Does anyone else come in? Let me find you. There you are. Okay. I'm having a few problems here. Let's see about sharing the screen again. All right. All right, I'm going to have to minimize this for a moment. I want to minimize this too, but I don't want it to go away. Let me do this. There we go. I'll open this back and see if maybe it'll come back on. Okay. Okay. Let's get this started again. Well, I don't see that PowerPoint. Why is it not showing up? Okay, let's see if my pen works. Yeah, well, it does. I think it did come back. Now the question is, can you see the pen? Can you see the screen now? I just put a little red mark on it.
I don't see your screen.
Okay, that's what I need to fix now. So let me minimize that. I don't want to discard it. Oh, okay. Now let's go back to this and return to meeting. But I'm not, okay, maybe that whiteboard. All right, here we come maybe. Okay. Zoom is not responding. I don't know what that means. I can't get. Okay. Let me see if I can get my. This is a pain. Okay. Sorry, Jamel, you got here and things start falling apart. Is it your fault? No, I don't think so. Let's try meeting controls. Okay. Can y'all see my screen now? A whiteboard?
Yes.
Okay. Let me see if I can. Oh, I can write again. Okay. So let me. Trouble is, I don't know how to do an eraser on this one. Okay. Let's see if we can go from here. Where we were writing before was sound. I don't like having that little pen there, but I'll live with it. Refers to. Oh, I think I see. Oh, here's an eraser. Whoops, didn't take. There we go. Let's go back to text. Nope. Draw. Well, nope, that's not what I want. Nah, goodness gracious. Why did I ever get out of it? Okay. I'll try to erase this. All right. See, I didn't use this whiteboard from Zoom before. I was using my own, but I can't get it to come up. Where is the pen? Anyone have any idea? I would think text would be it. But that's the text box. That's for me to type in. I guess I could do that. My typing's so slow. Let's try that. Let's erase that and erase this. And this will be really pathetic, but let's try it. Let me see if it'll type. Nope. I guess I need a box. Okay. Okay, sound refers to those waves transmitted through a medium with frequencies, if I could spell, or type, that was more likely, capable of being detected by the human ear, I think is what it is. Yeah, by the human ear. All right. Obviously, some human ears are better at detecting some sounds than others. I'm hard of hearing, so there's certain frequencies I have a terrible time trying to hear, as y'all have noted already. That's what sound is. Now, there are different animals have different ranges of frequencies that they can hear. Dogs can hear at, I believe it's a much higher frequency than we can, because a dog whistle can irritate the fool out of them and we can't hear a bit of it, okay? And there are other things like that that are going on. So, but we usually refer to human ears that you do. Now, someone remind me what the speed of most electromagnetic radiation is. Remember? Speed of C, speed of light, 300 million meters a second. That's the speed of light. I think I was telling y'all at the end of the last class, if you flashed the light beam and it was able to go around the globe at the equator, it could go about 4.5 times around the equator in 1 second. I mean, it's incredibly fast. We think of it as being instantaneous. It's not. It's just incredibly, incredibly fast. Sound, however, is not nearly that fast. Okay, whereas, let me do another box here. Okay. C, the speed of light, is equal to 300, 000, 000, meters per second. Okay? The speed of sound, its speed, maybe I should put speed of sound. Okay? Just to give an idea, is equal to something on the order of 331 meters per second. Okay? Quite a big difference there. A different order, excuse me, order of magnitude of approximately 1 million. Light travels at 1 million times the speed of sound. Okay? But this is speed of sound at that speed is only in dry air at 1 atmosphere of pressure at 0 degrees Celsius. Okay, today we're much warmer than 0 degrees Celsius. We're probably close to 40 degrees above 0 degrees Celsius. Okay, we're also probably fairly humid. That's not going to change it a lot, but it will change it a little bit. And we're pretty close to 1 atmosphere of pressure. Okay, changes of humidity and temperature cause a variation in the speed of sound, and the speed of sound increases with temperature at the rate of now speed of light is constant, but the speed of sound increases with temperature at the rate of 0.61 meters per second per degree Celsius. I don't have a degree symbol there, but degrees Celsius. I'll put DEG Celsius. Whoa, where did that come from? Okay, per degree Celsius. Now that's not very fast, is it? 331 meters a second, but then for every degree Celsius you go up, like I said, today was about 40 degrees Celsius above 0. 40 times 0.61 would be right around 2.5, not quite, but somewhere close to that. So then their speed of sound would be 333.5 meters per second. It doesn't change it much, but it does change it a little bit. Okay? So here are the formulas. I'll write them here. I'll try to, there we go. Here are the formulas. You have them in the book there. Oops, can't do that. V is equal to 331 meters per second plus, and here's the one we just did, 0.61 meters per second per degree Celsius. Okay? Times your temperature Celsius. So whatever the temperature, like I said, we increase by 40 degrees, multiply that by 0.61. Now, if you're dealing with Fahrenheit, then the velocity of sound in air, okay, would be 1,087. That would be feet per second. That's for U.S. customary, feet per second. A foot is about, a meter is about 3 times, a little more than 3 times a foot. So that's why if you look at it, 331 times 3 is going to be a little bit greater or a little bit less than 1087. But because a foot is a little more than a foot is a meter. 3 feet is a meter. I can't talk. And then you're going to add to that the change in temperature for Fahrenheit is 1.1 feet per second per degree Fahrenheit. Okay. And then you multiply that by, you close this parentheses and multiply by another parentheses your temperature in degree Fahrenheit minus 32 degrees Fahrenheit. Okay. Now, the reason for that, I'm going to go back and put a couple more spaces in here. Okay. The reason for that is above freezing. Now, freezing in Celsius is 0 degrees Celsius. Okay? Freezing point of water. So it's whatever your temperature is in Celsius, that's what you have. Now, if it's actually below freezing in Celsius, then this becomes a minus. Your speed of light actually slows down some. But because it's above and below freezing of water, water freezes at 32 degrees Fahrenheit, so you have to subtract 32 from whatever your Fahrenheit temperature. Like, I'm guessing it's about 80 degrees outside now, so 80 minus 32 would be 48. So 48 times 1.1, let's just say that's about 55 or 60, and add that to 1087 feet per second, and you would have what the speed of light in U.S. customary units, feet per second, would be on a day like today. Again, it's not a big change. Okay? Now, let's see if we can do another box here. There we go. Example 1. Find the speed of sound in dry air. We usually don't have dry air here in the southeast. Okay? At 1 atmosphere of pressure, that's probably pretty close to where we are, if the temperature is 23 degrees Celsius. So your capital T here is 23 degrees Celsius. Okay? So your formula would be this one up here. And that would be, okay, you tell me what to write down. You would use the top one, 331. I'm going to leave off the units, well, if I could write. 331. I'm going to leave off the units just because I want to fit it all in one line. Plus, because we're above freezing, 0.61 times degrees 23 degrees Celsius. I'll leave off the units. So if you got a calculator, someone pull it out and see what you get. Today I happen to have my phone with me. Usually I leave it in the vehicle because I don't like it going off when I'm teaching. But I needed something to keep up with time, so I'm using this now. And if I can find my calculator in here. Does anyone have it already? 331 plus 0.61 times 23 equal. Wrong. No. Yeah.
I got 345.03.
That's exactly what I got too. Okay. Good deal. Was that Rance? Or who? Huh? Who was that?
Rachel.
Oh, Rachel. I didn't even know you were there. Which Rachel is it?
Sullivan.
Sullivan. Got it. Okay. Now help me out. Has anyone else joined the class? Because this is how I do attendance. I can't tell any other way. I've got one sorry pen.
I'm here.
Say again?
Taylor Wells is here.
Taylor Wells is here. Got it. Anyone else? Okay, now so far I have Tamika. I have Rance. Tamika, I have Rance, Pettigrew, Jamal, Rachel Sullivan, and Taylor. Anyone else there that I didn't catch? Okay. And as you said, this equals 345. And because we only have 3 significant degree digits here, we're just going to leave this as 345, and that'll be meters per second. Let's see if I can get that in. Okay. What I'm going to do is see if I can do this. There we go. 345 meters per second. As you increase the temperature above freezing, you increase the speed of sound in air. All right, good deal. Let's see what the book got. Hey, look at that. They got 345 as well. Now, I'm surprised they did because the 0.61 is only 2 significant digits. The 23 was only 2 significant digits, and yet they gave us 3 significant digits. So I'll take it. Actually, it's okay because this answer will be 2 significant digits. That would give you, however, and then when you're adding, it's okay. All right. Now, example 2 is coming up. Let's do a box down here. For those who just came in, my pen quit writing well, so I have to use this box and type things in, and this is awfully painful. Okay, what is the time? So this time we're looking for time. Okay, that's what we're looking for. That's the unknown here. What is the time required for sound from an explosion to reach an observer? I'll do the distance here that it's trying to go is what? Okay, yeah, this is fine. 1900 meters away. 1900. And that last 0 is your significant digit. So there's your distance in meters. Okay? So we're looking for time. Well, we're using the data which we just had, which was that the speed of sound in the air at that temperature was 345 meters per second. Now this is drawing from a formula from an earlier chapter. I don't remember, yeah, I'm pretty sure we did it, but we didn't do many examples with it, I don't think. Does anyone know what the formula would be? It relates time, distance, and speed. I bet you know this because you, when you've gone on trips, you've used this very thing to calculate how long you're going to take to get there. What would be the formula? Anybody know? I bet you do. Isn't it distance is equal to your speed multiplied by your time? Isn't that what you do? I hate to put an X in there, but I think I will. Speed times time. Now that's not a variable X, that is a time sign. Because if you're going 60 miles per hour and you drive for 2 hours, how far do you go? 60 miles an hour for 2 hours. What's your distance? Help me, somebody. If you're traveling at 60 miles per hour for 2 hours, how far do you go? 120. You multiply, right? So how do we get to time? If you want to isolate the time, divide both sides by velocity. So time is equal to distance divided by velocity. Does that make sense? Let's see what that gives us. The distance was 1,900 meters. I'm going to have to expand my thing here. I'll probably leave off the unit, okay? Times, I'm going to expand my box here, okay? No, not times, divided by velocity, 345, oh, wait, I'm going to put my meters in. Meters divided by 345 meters per second. Okay, I'll expand my box again. Okay, now, here's what I want you to notice. Oh, I can't do this with that thing. Well, maybe I can. Okay. This is frustrating. Okay, I can't do it, but the meters would divide out. Do you see that? Okay, because you got meters over meters per second. So pull out your calculator and do the number part, and that would be I'm having trouble with my phone even. Okay. Has anyone done it already? 5.507, is that what you said?
Yes.
Ah, yes, I like it. Okay. And so let me write this. That's one bad thing about having to use this. 5.507. And that would be in seconds. Now that's the part I wanted you to see. Let me expand this. Okay. Because the meters cancel out, then you're left with 1 over 1 over second. And when you do that, 1 divided by 1 over second, you flip the second one and you get seconds. and that gives you 5.5 seconds. And in fact, I'm guessing they would probably round this to 5.51. What do they do in the book? Yeah, that's what they do. They, whoops. Because you only have 3 significants there, 4 there, you can only have 3 here. So that last digit was a 7, round to 0 up to 1. 5.51 seconds. Does that make sense? And that's what they got there. All right. I'm going to end this slide. Let's see. Tell you I already had you. Okay. And I'm going to go back to I've lost my other PowerPoint now. I don't know where it went. Okay. Let me minimize this. And goodness gracious. Somewhere up here I've got my, there it is. Oh, I know where I could have gone. Let me end this one. I think right there is where I could go. Yeah, there we go. This is really a pain. Okay. Okay. Now, can y'all see the electromagnetic spectrum? The one that I had up earlier. Yes or no? No, I was afraid not. Okay, let me minimize this and go back to this. This is such a pain. All right, return to meeting. Didn't know it ever left. Okay, and somewhere down here, okay, I want to get, here we go, share screen. That's what I've been looking for. Okay. I don't see it, but I'll go to, oh, Chapter 16 PowerPoint. That's the one I want. Okay. From current slide. Can y'all see this now?
Yes.
Okay. You can see the electromagnetic spectrum again?
Yes.
Yeah, okay. And let's see, I already got them all here, right? Yeah, I'm pretty sure I did. Okay. Anyway, here we go. Finally. The speed of sound in a variety of different menus of media. Okay. Aluminum, quite fast. Brass, a lot slower. Now this is at normal temperatures and pressure. Of course, these being metals, they go very fast. Steel, very fast. Granite, very, very fast. Alcohol, much slower. Water, much slower. Air, 331. Look how slow it is in air. And those are the numbers, remember, we saw earlier. 331, and in our green box, it was 1087. They rounded to 1090 here. But a vacuum, it doesn't go at all. Okay? Sound does not travel through a vacuum. Why is that? Because sound is one of those longitudinal waves that compresses the air waves. Okay? It's not If there's no air, like in a vacuum, there's no sound. Absolutely no sound. That's why when the astronauts are out there in space, even if they didn't have those heavy suits on, they couldn't communicate with each other except by radio, because sound will not travel when there's no air. But notice air is the slowest medium out there. Water, alcohol is next slowest, but it's still almost 4 times faster than the speed of sound in air. Water is more than 4 times, close to 5 times faster, but then your metals are really fast. Now, I don't know if any of you were fans of the old Cowboys and Indian movie, or the bank robbers and stuff, train robbers, those kind of movies way back when you were young. But on that, when the trains were coming, the good guys or bad guys, whichever they happen to be, to know when they're coming, they put their ears down on the rails. Why? Because steel transmitted sound much faster and much more efficiently than it went in air. So they would hear the train miles away when it was on the track than they would through the air. Much further through the track than into the air. So those are just some of the speeds of sound. Now you're going to be dealing with sound traveling through mostly water. That would be human tissue, okay? So that's the one you'll probably be more interested in, if you're interested at all, okay, in sonography, okay? So let's see what the next slide is. That's coming up a little bit later. So let's see if we can go back to our graph PowerPoint. Now we're going to try again and see if I can write on it this time. Can y'all see that one? The white screen? You can? Okay. Let's see how we do on this. Here are several of the characteristics of sound. Okay? I don't know if these are important to you in sonography, but they are important in physics, okay? Now, why did that show up? I don't know. This is frustrating. I'm afraid if I just lost it. So now I got to go get it back again. Word. Rachel, you're in the way here. No, I'm just kidding. Got to minimize that so I can get my PowerPoint back where I left off. Current slide. We'll go with that. Now, let me make a guess. Can you see that? The white screen?
Yes.
Oh, all right, good. Okay. I think I've already got Tay here, so I'm going to move you right up to the corner here. Okay. And let me get my color back. This is where it bottomed out last time. So let's look at some of these features. Intensity. Okay. That basically is the energy transferred energy transferred by sound per unit time, through a unit area. Okay, that's what intensity is. Power per area. Okay. Now, what is power per area? Energy per time is power. Energy divided by time is power. Now, this may be important to you, so this is power then per area. Because it may be that in doing your job, you're going to have to set the intensity levels, and that would be probably measured in something like kilowatts. That would be power per area, per meter squared, possibly for square centimeter. I don't know. Okay? Loudness. Sorry. Refers to the strength that's an H there, it's not a very pretty H, of the sensation of sound heard by an observer. Okay? That's your sensation. It's related to the intensity, for sure. Okay? It describes how faint or how loud the sound is. And a guy named Alexander Graham Bell, who's featured there on the left, he came up with a way to measure this, and they actually named the unit after him. Now, they didn't spell it the same as he did. They named the unit the Bell, B-E-L, okay? But because Bell is a fairly large unit, we usually do 1/10 of a bell, which is called a decibel. Have you ever heard of that? Sound referred to in decibel, okay? And that's where the next slide comes from. But before we get there, let's make one other definition here, and this is pitch. Now, pitch is different from intensity and loudness. It's the effect of the frequency of sound waves. Are any of you singers? Or you like to hear singers? Okay? Sometimes you'll hear someone referred to as just a tremendous singing voice as having perfect pitch. Now, what that means, this is my interpretation of it because I haven't ever seen a pure definition of that. Let me start by asking this question. Have you ever heard yourself on a recording that somebody has hidden a tape recorder and tape recorded the discussion that was going on and then played it back? Ever had that happen to you? Yes or no? Did you recognize your own voice? Anybody?
No, it sounds a lot different.
Yes, exactly. You recognize everybody else's voice, though, didn't you? But your voice? This happened. We had a good friend of our family gave us one for Christmas, but he didn't tell us he was giving us a tape recorder. He just brought it in and put it under the table with no one noticing it as everybody sat around and talked. It was mostly he and his wife and my parents, they were sitting there talking. And then he pulled it out and played it. And my poor mom, she said, "Well, who's that doing all the talking there?" She recognized everybody else's voice but her own, and she just gave it away that she was doing most of the talking because she did not recognize her own voice. That's because when we talk, we hear the vibrations that come through our bones, in our head, in our thing. We hear that because that's closer to us. When we hear anybody else talk, that's the sound coming through the air that enters our ear. So we'll recognize everybody else's voice, but we do not recognize our own. Or if we do, we think it sounds terrible, okay? So someone with perfect pitch, obviously what they are singing is what everybody else is hearing because they can hit the notes right on and it sounds right to them, okay? Now, I've never heard that defined that way, but it's the only way I can figure it out. So with that in mind, let's go back, even though this takes a long time to do, and go back to the other slide, which is this one. Okay. All right, can y'all see that one?
Yes.
Good. Okay. Here are some of the intensities, the range of sound levels and intensities. And one thing I really want you to notice is the amazing ability of our ear. The threshold of hearing is 0 decibel. Okay, that's as low as anyone can hear, basically. That's an intensity of 10 to the minus 12 watts. That's the unit of energy per square meter. And by the way, a watt is a very small amount of power, and a square meter is a huge area. So this is an incredibly small number. 10 to the minus 7. That's scarcely audible. I can almost guarantee you I will not hear anything at 0 decibel. Now, minimal sounds, they will be around 10 decibel or 10 to the minus 11. Now, one thing to notice about this scale here, okay, you'll notice the, let me get my pen back. Hopefully you'll notice this. Okay, when you go up 1 power of 10 here, from 10 to the minus 12 to 10 to the minus 11, you go up 10 here, 1 times 0. Go up another one, you go up another 10. Another one, you go up another 10. This is 1,000 here. This is 10 here. What this is called and it's a decibel. If you measured this in bells, you would move the decimal over 1. That would be 0, 1, 2, 3, 4, 5, 6, 7, 8 bells, and they would be 1 power of 10. Okay? This is a log scale. Well, yeah, it's a log scale, because when you go from 10 to the minus 12 to 10 to the minus 11, you're going up a power of 10. Whereas in the bells, you're going up 1 unit. That's what a log scale does. It takes a wide-ranging scale and narrows it down to a smaller number. But we use decibels, so we add another 0 to it. Okay? So minimal sounds are at 10 decibel or 10 to the minus 11 watts per meter squared. A ticking watch. I don't know the last time I heard a ticking watch. I have heard it sometime in my life. 10 to the minus 10, which is another factor of 10, but it's a level of 1 bell. That is 20 decibel. Okay? A whisper, 30 decibels. I can barely hear a whisper. Okay? Very faint sound. Average home, neighborhood, street noise, that would be around, leaves rustling, a refrigerator kicking in, that would be around 40 decibels. I'll hear maybe a little bit of that, but not much. Average home, neighborhood, street, moderate, around 50 decibel. Yeah, I'll hear most of that, except sometimes I can't make out what the noise is. Like if my wife says something, I can hear her saying something, I just can't make out what she's saying. Okay, she calls it selective hearing loss, but that's beside the point. Okay, normal conversation, around 60 decibels. I sometimes, in a normal conversation, have to ask people to repeat things. Again, it's not because I don't hear that they're talking, it's just that I don't distinguish well enough to tell what they're saying. It's just not quite loud enough. A car alarm clock, city traffic, 70 decibels. There are some mornings I do not hear the alarm. My wife might be in the other room and she'll say, "Your alarm's going off." She'll have to come back and say, "Did you know your alarm's going off?" No, I didn't. Okay. Now that's because I sleep heavy, but it's not just because I'm hard of hearing. But indeed, one ear is worse than the other. If that's the ear up, I'm not going to hear the alarm clock. Garbage disposal, vacuum cleaner, outboard motor, noisy restaurant. Yes, I'll hear that. That's called very loud. that's normal to me. Okay, that's about the normal range I hear well, around 80 decibels. Factory electric shaver, screaming child, around 85 decibels. Lawnmower, passing motorcycle, a convertible ride on a free road, around 90 decibels. Hair dryer, diesel truck, chainsaw, helicopter, subway train, around 100 decibels. Maybe one of the reasons for my hearing loss is when I was younger, we used to cut our own firewood back on the farm, and I was around chainsaws and other very loud noises that may have hurt my hearing. A car horn, snowblower, I'll hear those most of the time, though I don't hear snowblowers often in the South. That's 110 decibels. Rock concert, prop plane, don't want to hear those, but that's going to be around 120. That can be painful, okay? Deafening was at 110. And then 100 feet from a jet engine, you don't want to be there. You better have on sound suppressors if you are. Air raid siren, which would also be your warning sirens for bad weather, around 130 decibels. A shotgun blast, I don't want to hear either, around 140 decibels. Okay. Now, while we've got this here, let's go to the next slide, which is the next thing the book is going to talk about. Okay? All right. And this is the human ear and how it's put together. And y'all, I think a lot of you are from, getting a little dark in the room. So I turned on the light. That's how I got further from the microphone. The human ear you see here, I'm not going in great detail. You probably know it better than I do. But this is the external part of the ear, the part you see, but that also includes the external auditory canal, which you don't see, but you deal with, especially if you've ever had anything like swimmer's ear or anything else. That's a fungal infection in that external auditory canal. It's internal, but it's not what they call the inner ear, or even the middle ear. The middle ear starts basically at the tympanic membrane, which we call the eardrum, okay, and then goes in from there. And there you have the malleus and the incus, okay. Those amplify the sounds that the eardrum is what picks up those little tiny vibrations of the sound going through the air and transmits those. Now, I want to point something out to you. You notice this tissue here? That's bone. All around here, you're surrounded by bone. That's what's transmitting the sound that you hear of your voice. That's not what you hear with other people talking. You hear what comes in the membrane. In the canal. So that's why you don't always sound like you think you sound. Okay. This part here is called the stapes and oval window, okay? This, I guess, is what they call the oval window, and this is the stapes, which, again, amplify the sound coming through the middle ear. Then you get to the inner ear. What the inner ear is this, it looks like a seashell, doesn't it? That kind of seashell is called a cochlear seashell. And that's why they named this the cochlea, okay? Again, things are getting amplified here. Now, inside this structure here, you have these tiny, tiny, tiny little fibers. And those are what vibrate, and that's what sends the signal to the nerves. So incredibly fine sounds can be transmitted picked up, and your cranial nerves pick it up, take it to the brain, and the brain makes sense of it. Now, what happens with me and older people in general, the little fibers, the little cilia, they call it, little strands that are finer than hair that move around in here, they either wear off, break, or just get stiff, and we don't pick up and understand sound as well, okay? And that's why we have hearing loss. Now, this is a eustachian tube. I don't know if any of you realize what that's there for. Does anyone know? Anyone want to make a guess? Eustachian tube. Okay. I take it not. Okay. That's to equalize pressure. Have you ever gone on a plane ride? I'm guessing most of you probably have. Or else ridden in a car up into the mountains, especially going at a fairly good rate of speed where you're changing altitude pretty quickly. What happens is as you go up in altitude, your pressure is dropping because you have less atmosphere above you, less weight of the atmosphere, and pressure is force per unit area, weight per unit area. You have less things. So your pressure decreases. Well, when the pressure decreases, all you got out here, inside your body, it hasn't decreased. Outside it has. So you start blowing your eardrum. It starts protruding outward. You need something to equalize the pressure. And what they recommend for you to do is hold your nose and blow or something like that. I find just opening my mouth really wide opens up this little opening here and allows you to equalize pressure better. Now, if you've ever been on a plane ride when you've had severe congestion, that can be incredibly painful because your eustachian tube might swell up and you can't relieve the pressure, and now you risk puncturing your eardrum by the change of pressure. If you've ever been on a plane with a very small child, you probably realize you were on a plane with a very small child because their eustachian tube is so incredibly tiny there, they don't balance pressure well at all, and their ears will send them screaming. Okay? And usually the act of crying equalizes the pressure, but then they usually don't stop. They got into a groove of crying and they usually don't stop. But sometimes it will help them. So you really do want them to cry some, but you do want them to stop. Okay? Now, kids who have chronic infections like that, and their tubes stay so congested, you might say, that they don't allow enough air through, they have to have tubes put in their ear to go into here to help equilibrate the pressure, that hold that open to allow enough air to pass so that they don't have those chronic earaches. So anyway, way more than you probably needed to know, but that, since the picture was here, we did it. Now, let's move on to 16.4, and this is the Doppler effect. Okay? I'm going to risk it, okay? Found out this is the best way to go, I think. Okay? Yeah. Can y'all see that now? The white screen again?
Yes.
Good, good. Okay, I think I've got this down now. What is the Doppler effect? Okay, I got to get my pen back. Okay, the Doppler effect remember this. Sound is a pressure wave, right? As what's happening with sound is that say when you're talking, hold your hand in front of your face, and when you're talking you can feel the little puffs of air hitting your hand. That's a pressure wave, okay? Now, those little puffs of air, those are the crest, remember? When they're concentrated, those are the crest. If you're in a moving object, then the crests are getting pushed closer and closer together. If the object is coming toward you. If the object's moving away from you, the crests are getting further and further apart because the object is moving away. Okay? And that creates a change of frequency. So the Doppler effect refers to the variation of the frequency, okay, I already had T here, right, okay. The variation of the frequency heard when a source of sound and the ear are moving relative to each other. Now, let me say this, are moving relatively rapidly near each other, toward or away from each other, relative to each other. If you're just moving slowly, you're not going to notice any change in the frequency because you're not moving anywhere close to as fast as the speed of sound. And you don't even have to be all that close to the speed of sound, but you're moving so slowly, okay? So you only are going to notice the Doppler effect when either the source or the receiver is moving fairly rapidly. The classic examples of this are either if you're at a train track and you hear a train coming and the train is blowing its whistle or doing something like that, as it's coming near you, of course it's going to be getting louder because you're getting closer to the sound, but you'll also hear it go up in frequency because the wave fronts are getting closer to each other, okay? So it will be going, increasing in frequency. If, however, the train is moving away from you and blowing its whistle, it will, number one, it will get less loud because, it's moving further from you, but you'll also hear the frequency go down, like, going in that direction. Now, those are terrible sounds, but you get the general idea of what I'm talking about. This also holds true for police sirens, fire trucks, anything that's going at a relatively high rate of speed, either coming toward you or going away from you while it's emitting the sound. We think that sometimes it's changing its frequency. No, it isn't. It's the fact that it's moving relative to your ear. Now, this was named after Christian Johann Doppler, who was a physicist and mathematician born in Austria, and best known for this explanation that he gave here. It's been years since I've seen an episode in this, but when it first came out, I remember occasionally watching The Big Bang Theory. And it had a lot of garbage in it, it was a comedy, and that's all it was really intended to be. But incredibly, it had a lot of science in it as well, okay? And most of the science was pretty good. They had, in fact, one of the stars of the show is I think maybe a PhD in some sort of biology or chemistry or something, okay? She's quite good. She knows her science. And the people who write the show know their science. Now, most of the show is not based on science. It's relationships and silliness and stuff like that. But the science part of it is really not too far. But I can remember one episode I saw years ago when Shelton went to either a Valentine's or some sort of party, and he wore a t-shirt that had lines, wave fronts, getting closer and closer together. And people said, "You were supposed to come in costume." He said, "Yes, I did. This is the Doppler effect." Okay. Of course, they didn't even know what the Doppler effect was, and they certainly couldn't recognize what that was supposed to be represented. But here is the formula that gives you the apparent Doppler shifted frequency for sound when it's moving. So here's the formula. F prime, we're going to talk about what that stands for in just a minute, is equal to F multiplied by V, and we'll talk about what that stands for, divided by V plus or minus V sub S. Okay? Now, let's hit what these various things is. F prime is the Doppler shifted frequency. It's not an actual frequency, it's the shifted frequency that we are hearing, but it's not the frequency that the siren, the horn, the whistle, or anything else is making. It's the one we are hearing, the Doppler shifted frequency. F is the actual source frequency. So that's actually the frequency that the whistle, the siren, the bells, or whatever it is making. That's the F. V, both of these V's are the speed of sound. Now the speed of sound is that speed that we did the earlier formula on. The 331 plus 0.06 times t, 0.61 times t, or 1087 feet per second, plus 1.1 times t minus 32. That is the speed of sound. The speed of sound adjusted for temperature. Okay? Now this one, the V sub S here, is the speed of the source. That could be the speed of the train, the speed of the fire truck, the speed of the police car, the speed of the ambulance, whatever is making that sound that is being shifted because it's coming towards you or away from you. But here we got a problem. Why do we have a plus and a minus there? Which do we use? Well, that depends on whether the source is going toward you or away from you. Okay, so the plus sign here, the plus sign in the denominator is used when the source is moving away. When the source is moving away from you. The minus sign is used when the source is coming towards you, moving toward the observer. Okay? Now here's the way I remember this. And that's because I do math, okay? When your denominator increases, your frequency decreases. The apparent frequency, the shifted frequency decreases. And that would increase when you add those two. Because, see, these two V's are the same. What you're doing when you add the two, you're making the denominator bigger. So that makes the frequency smaller, the apparent frequency smaller. The actual frequency doesn't change. But when it's moving away from you, moving toward you, that you subtract the speed of source from that, that makes the denominator smaller, which means makes the shifted frequency higher. So that's what you're hearing when the pitch goes up, and the plus is when the pitch is going down, when it's moving away from you. So that's kind of backwards seeming. The plus is when it's moving away, the minus is when it's moving toward. So just remember, it is a little on the backward side. Okay. Here we leave again. Okay. And go back to chapter 16 PowerPoint. And go back to current slide here. Okay. Here is the illustration of what we're talking about here. Okay. The car is coming to you, especially at a fairly rapid rate of speed, and blowing the horn. You, person A here, it will sound like the horn is going up in frequency. Okay? Observer A is in front of the car. Here's the car horn. Okay, I have to move T a little bit here. Okay, there we go. Observer A is in front of the car. Here's the car horn at a higher pitch than the driver would hear it, because the driver hears the actual sound of the horn. So because the frequency of the horn is a very regular circle here, okay, because he's going here, this one hears the higher frequency. Person B back here is hearing a lower frequency because the car is moving away from her. Okay, so observer B hears a lower pitch than the driver would hear, and certainly a lower pitch than person A would hear. Okay, does that kind of make sense? All right, that was it for that slide. Let's now go back to this one. Okay, and from current slide. And get our pen back. Now let me know if you ever fail to see the thing. I will see it, but you may not see it. So let me know if you can't see the slide that I'm working on. All right. Example 1. An automobile sounds its horn while passing an observer at 25 meters per second. What is that a measure of? Now we had several symbols in that last example, in that last equation. Which symbol does this represent?
VS.
Say again?
VS.
V sub S, perfect. That's the velocity of the source. Meters per second lets you know it's a velocity, and because this is the vehicle, the automobile, that is the source. Okay, excellent. The actual horn frequency is 400 hertz. So that's a frequency of 400 hertz. Now 400 a hertz is a per second. Okay, that's what a hertz is. Did I use the right symbol for that? Is F the symbol for the actual frequency?
Yes.
Yes, so that is the correct symbol. Okay, assume that the speed of sound is 345 meters per second. Okay, that sounds like a speed to me, and that's 345 meters per second. Sounds like the same one we were using earlier. What was that? Around 23 degrees? I believe that was it. Is that the right symbol for that?
Yes.
Really? Yes, you're right. That's the speed of sound. The speed of the source is V sub S. The speed of sound is actually V. You're absolutely right there. Okay? So, with that in mind, what is the frequency heard by the observer? Now, what frequency will that be? This is F prime, exactly. That's the observed sound. Okay? The what was the word they used for it? Perceived, I believe it was. The Doppler shifted frequency. Okay, that was it. Doppler shifted frequency. That's what we're looking for. And what was its formula? Help me here. What was the formula for Doppler shifted? Okay, V sub S. That's what I think I heard you say. Okay, the A part says, what is the frequency heard by the observer when the car is approaching? So this is A for approaching. Which symbol do we use, plus or minus?
Minus.
Yes, we use the minus. It's sort of backwards seeming, but that's the one we use, the minus. So now all we do is plug and chug. Okay? Your frequency is 400 hertz, which is per second. That's your unit there, times your velocity of sound is 345 meters per second. We'll go with that, divided by 345 meters per second, minus, you told me to use 25. What is that, meters per second? Okay. So that's going to be 400. You know what? We're not going to use that. So let's just call it hertz. Okay? We'll just call this hertz, because that's not going to change here. That's going to be the observed frequency as well. So we'll leave that as hertz. 400 hertz times 345 meters per second divided by, what's 345 minus 25? Y'all can do that in your head, can't you? Huh? 320 meters per second. Now notice what happens there. These units cancel out completely. That's why I could leave hertz alone there. So if you pull out your handy dandy calculators and do, mine is really slow because of operator error, okay, 400 times 345 divided by 320 equals, what you get the Doppler shifted frequency to be.
I got 431.25.
Okay, let's just round it to 431 hertz, because that's the unit. So it actually was 400 hertz, but to that observer standing in front, it sounds like 431 hertz. The Doppler shifted frequency was that. Okay? Now the B part says, that is while the car is approaching. The B part says, what is the frequency heard when the car is leaving? So the car is going by you, still banging down on the horn, and it's driving you nuts. That would be F times V over V which? Now the car is going away from you. Plus V sub S. So we use the same numbers, 400 hertz times 345 meters per second divided by 345 meters per second plus 25 meters per second. And that would be 400 hertz times 345 meters per second divided by what now? Anybody? 345 plus 25.
370.
370 meters per second. And again, these meters per second go out. And what's your perceived or Doppler shifted frequency now?
373.
373 hertz. Did I write down the, yeah, I wrote down the other, 431. Let's see how the book did. Look at that. They got them both right. Good for them. Okay? All right. They have a little blurb at the bottom of a thing you can play with a horn. And then they have a physics connection dealing with, guess what? Ultrasound. However, this is obstetric ultrasound, and I think y'all said y'all were all going to be trained for cardiovascular ultrasound. Is that right? Guess what? The principles are still the same. It's just the frequencies, those kinds of things will be a little bit different, and your techniques, I'm sure, will be different. But here is problem set 16.4. I would do some of the odds, 1 through 5, if those answers are in the back of the book, and then do some of the others, 7 through 19, any of those, if those answers are in the back of the book. Okay. Oh, no. It can't be we're in a minute of being through, is it? Okay, before anyone leaves, let me find out. Did anyone else show up besides, let me read through the names I have. I have Tamika, I have Rance, I have T, Jamal, Rachel Sullivan, and Taylor. Was anyone else present today besides those 1, 2, 3, 4, 5, 6? Anybody? Okay. Those will be marked present. The rest of you will not be. So, now, did any of you have any difficulty getting in?
No.
Does this seem to work okay with y'all?
Yeah, it is.
Okay. So every Wednesday, except of course, you know the good news, bad news next week, right?
Spring break.
Yeah, the good news is it's spring break, but the bad news means we won't be meeting next Wednesday night. Sorry about that. Get over it. Okay, but the following Wednesday, we will be meeting for certain. Same time. I'll try to have it all set up by 4:30, and we'll get started right at 4:30 and go from there. For those, they're saying they think we'll be back the next week. I don't think so. My wife's an infectious disease epidemiologist, and she doesn't see any way that the numbers are going to come down anywhere close enough for us to be back that next Monday. So I would not bank on being back the following Monday. If we are, well and good. But if not, so for certain next Wednesday, which will be, I believe, what's that, the 1st? April Fool's Day? Is that right? I think so.
Yes.
And we'll be meeting again, just like we did tonight. And then the next time we'll know something before the next time. All right? Well, be safe. Have a good spring break, but don't get into crowds. Don't get into any kind of crowds. Use social distancing and lots of hand sanitizers, alcohol swabs, whatever it takes. Try to keep safe and keep healthy. Okay? All right. We'll see you in 2 weeks. All right. Bye-bye. Yes. Okay, now say that one more time. Oh, you have test number 2. Is that what you said? Ready to turn in? Okay. What you can do, can you scan it and send it to me via an email? Okay. Why don't you do that then? That'll be the easiest. Now, if you know how to load it on Blackboard, we might be able to do it that way, but I think scanning and sending it by email is probably going to be easier for you and probably for me too. Which would be easier for you, okay? All right. Did you get a copy of the, what was it, the 3rd test? You did, okay. Chapter 12 test? Okay, good. So then you're set. So if you'll just send me that 2nd test, I will get it graded and put the grades out on Blackboard. Okay. Any other questions, by the way?
So do you want us to do the same when we finish the chapter 12 test?
Absolutely. As soon as you finish that, you can scan it and send it to me. Unless, of course, you know how to load it on Blackboard, I can get it that way too. But I think it's probably easier to scan it and email it to me. But whichever works for you, let me know. Okay? Any other issues? All right. Have a good, safe spring break and keep healthy. All right?
Yes, sir. You too.
Thank you so much. Bye-bye.